Okay, looking at adding on here to talking about our motion. We're going to be talking about now velocity and adding on to acceleration. So couple slides we're going to do here, a lot of fill in the blank stuff in this intro to velocity and acceleration. So velocity we know is speed, right? So when we say instantaneous velocity, that means the actual velocity at a specific time in question. We've talked about average velocity, right? Which again is on a time interval. From here to here, what was our average velocity? Instantaneous is at a single point, what was our velocity at that single point? Average velocity is useful to us because even if your velocity is changing over that time period, as long as your average actually stays the same, you're going to travel the same distance, yeah? If I'm going from 25 to 50, well, the average of that's going to be right in the middle of that. If I am going 0 to 75, the average is going to be right in the middle of that, and so it ends up being the same average. Now, terminology is important. If a question simply says velocity, it means instantaneous. If it says what is the velocity at this point, it means literally at that point. Otherwise, it will say average. There are situations where the instantaneous is the same as the average at all points, and so sometimes we don't care, right? If we have a non-change in velocity, the instantaneous velocity is the same as the average. If you look at the warm-up that's on your guys' slides, we're going to do this tomorrow, but instantaneous at t equals 8 versus the average from 7 to 9, well, that's right here. Yeah, t equals 8 is right in here, but it's all the same from 7 to 9, right? So sometimes it's kind of trivial to talk about it like that. Okay, so let's talk about constant velocity versus now changing velocity, varying velocity. So we saw an example in the previous lesson of constant velocity, which had evenly spread dots, right? That told us that every single, I'm covering the same amount of distance in the same amount of time. That's constant. So changing velocity means that we're experiencing an acceleration. So as time progresses, more distance or less distance, depending on the type of acceleration, is covered per second. So you can see these dots are spaced out differently, yeah? Closer here, further away here, closer here. Remember that the further away the dots are, that means you're going faster. Again, think about your sugar packets. If your sugar packets were spaced out super far away, that was because you were having to drop them every second further and further apart from each other. That's faster. These ones are going to be closer in here and slower. So here's what an XT graph will look like for this runner. What do you notice about this graph that we haven't had to work with yet? It's a curve. Notice that this does not create a straight line. So when there is on a position versus time graph, when it's not a straight line, that proves to us there's an acceleration. So if you want to make a note there, this is an important thing we're going to push. But on an XT graph, curves mean an acceleration. Because my position is not changing at the same rate. I believe it's acceleration. My position is not changing at the same rate. That's what creates the curve, yeah? If my position was changing at the same rate, my slope would be constant. My slope is not constant here, so velocity is not constant. So let's go ahead and make a note card for this. I'll go ahead and give you a second to copy this. Acceleration on the front side. We have the definition, the units, and the formula on the back side. I'll give you a second. Go ahead and pause the video, copy it down. And again, as always with the note cards, we're going to emphasize this in class. We're going to go over a bit more in detail, but I just want you to have that down for now. Okay, 2 more slides I think we're doing. Yeah, 2 more slides. Okay, so instantaneous velocity versus average velocity when we have acceleration. So when we have acceleration, it's difficult to tell the instant velocity since, by definition, the acceleration means we have a changing velocity, right? So we have a curve on this graph. We know that on a position versus time graph, the slope is acceleration. But if I have a curve, well, I can't do y equals mx plus, I can't do my slope formula on a curve. However, we can always find the average velocity by finding the slope between those endpoints. Again, the instantaneous velocity is hard to find, but I can do the average between 2 points. So we can see here I've got this curve, yeah? If I wanted to find the average from t equals 6 to t equals 24, I'd make a straight line connecting those 2 dots, find the slope. That would give me the average velocity. Again, we can see based on the curve it is changing, but the slope of this line is the average velocity. Yeah, and again, you can see that there. Slope is the average velocity. Now, this is going into calculus. If you've never taken calculus before, hopefully this makes sense to you. If you've taken calculus, you're going to know this word. Now, if we shorten the time interval that we take the average velocity on, again, we can see here it was t equals 6 to t equals 24, right? If I kind of squeeze that interval down, we can actually get closer and closer to the instantaneous velocity at the point we were looking at. You can see here I have an interval from t equals 6 to t equals 12 seconds now. That's going to be closer to the actual velocity right in the middle of these two. Yeah, this will give me a more accurate estimation than from t equals 26 to t equals 24. And you can see that, right? You see we have this gap here. Yeah, that's because it's a pretty, vague estimation, I should say. But as I make a smaller line, do you see how it almost follows the curve? That's because it's going to give us a better estimation. Now, really, in order to find the instantaneous velocity at a certain point, we would need calculus and something called a tangent line, which touches our graph at exactly the point we were referencing. So this is an example over here of a tangent line. It just touches the graph right there. It looks like, because again, it's hard for us to see, it looks like it might touch the graph more, but mathematically, actually, we can prove it, mathematically, it perfectly touches the curve only at that single point. And so the slope of that line actually tells us the instant velocity at that point. And again, you can see that over off the side here. I could approximate tangent lines at any point. So for example, let's go ahead and draw one. If I picked this point right up here, to draw a tangent line right there, I want to draw it so that it touches only that single point. So I might draw it close to, yeah, that's about a tangent line. Here, my tangent lines are going to be a lot steeper, and hopefully you can tell that. Now, the tangent lines here honestly look like they would be like the perfect curve, but a tangent line here might be something like this. Ugh. Yeah, that's pretty much a tangent line there. It's because it's a very, very, not a very curvaceous curve. It's almost a straight line. So again, the slope of a tangent line will tell us the instantaneous velocity. So we're going to watch this video in class to clarify it and kind of practice the concept of tangent lines a bit further. We will only ever be talking about the slope of a tangent line. You're not actually ever going to find it. It's just in concept. We would need calculus in order to find the actual slope of that tangent line. So again, in class, we're going to continue with this. A lot of upfront stuff. Hopefully, though, it's getting an idea so we can really push it further in class.